Want to start with what? 18. Why did we want to start with 18? Oh, come on. Why do we want to start with 18? Tell me why.
Can you do it without using a calculator?
Yeah. Of course you can do it without doing it. You can do anything without using a calculator, technically. You just tell somebody to use it for you. I don't know.
As long as you use the approximate.
Okay. You're supposed to do this limit. Can someone tell me what that says? It's the limit as x approaches. The limit as x approaches -1 of that thing, right? Yeah. So I've only given you a few things you can do. You could use a calculator. You could make a path. You could see what it's approaching. If you wanted, that's not 100% not accurate, but 100% sound. It doesn't prove it. How would you do it algebraically? What would you need to do? Absolutely correct. Difference of squares. Oh, great. Can you keep on factoring? Yeah, you can. What can you factor on? Oh, you still have a difference of squares right there. So what does that actually equal? X plus 1 squared over x plus 1 times x minus 1 times x squared plus 1. Now, what cancels? Does anything cancel? That cancels away. That cancels, and you're left with the limit as x goes to what? -1 of x plus 1 over x minus 1 times x squared plus 1 squared. What's nice about this? You can plug in -1, can't you? Right? You end up with 0 over. At this point, you just hope the denominator isn't 0. You end up with over what? -2 times 2. 2, and that's equal to 0. Done. You've just proven that the limit is 0. You've just proven that the limit is 0. And the entire key to this is factoring. You always factor. Factor, 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 factor. Removable discontinuity is definitely not a what? It's not an asymptote. If it's an asymptote, that's not a removable discontinuity. You can't plug that with one point. That's equal to the limit as x goes to 1 of 1 plus 3x over 1 plus 4x squared plus 3x to the 4th, all to the 3rd power. So that's the first, and I think they give you like numeric. This is limit law number 2 or whatever. I don't know the correlation in your book. Then you know that it's the limit as x goes to 1 of 1 plus 3x divided by the limit, and that's a bad way to do division, I know, but I'm just stuck doing one line. 1 plus 4x squared plus 3x to the 4th, all raised to the 3rd power. And then you could do the limit as x goes to 1 of 1 plus 3 times the limit as x goes to 1 of x, that quantity divided by the limit as x goes to 1 of 1 plus 4 times the limit as x goes to 1 of x squared plus 3 times, you see what I mean? X goes to 1 of what? X to the 4th, and then this whole thing is raised to the 3rd. Theoretically, there's a few things I could do here. Well, actually, well, 2 actually. You theoretically can then just, you could do the limit of this and then square it, the limit of this and then raise it to the 4th power. That's what they mean. You can break it down into its individual pieces. What's the limit as x goes to 1 of 1? 1 plus 3 times the limit as x goes to 1 of x. 1, right? Divided by the limit of 1 plus 4 plus 3. Thank you, not 4. 3. Yes, that's correct. So then you get 4 over 8 is 1 half. Oh, I cube this thing, yeah, you're right. Yes, correct. There you go. Oh, exciting stuff. Sound good? Okay, a function is continuous at a number a. A is an x value. If the limit of the function as x approaches that a value is the function's value at that point. Does a function have to exist at that point for it to exist? For it to be continuous there? Yes. It does, because is f of a defined if the function is not defined at f of a? No, that's an immediate contradiction, right? So, first of all, the function has to be defined there. But what that means is you're approaching a certain y value. The function itself has to evaluate to that value that it's approaching. For the limit to exist, does the function have to exist at that point? No, it doesn't. Can the function be anything you want it to be? You remember how we move that point up and down and it doesn't change the limit? Do you remember that, everybody? Yeah. It doesn't matter what it is, but for the function to be continuous, does the function have to be the actual limit value? Yes. Yes, it does. What that means is, here's the simplest way I can define continuity. A function is continuous if you can draw it without picking up your pencil. If you have to pick up your pencil to draw the function is not continuous. And where you picked up your pencil, it is not continuous there. Do you understand what I'm saying? So the technical definition is this. It means that f of a is defined, meaning for the function to be continuous at an a value, the function has to be defined at the a value. 1 over x, is that continuous at 0? No, because is the function, can you plug in 0? No. The limit as x goes to a exists, meaning the limit has to be the same on both sides, and the limit is the output value. What that means is, if I just had a function, and let's say I was looking at this point, here's x equals a, let's call this f of x, is the function f continuous at x equals a? Yes, for everything that you can see and deduce, it is continuous right there. Let's say I changed it just a little bit. Let's just say I took this, erased it from here, made an open dot, and put the dot down here. Is it continuous at a? No. Why? Okay, what's another way to say that? It's not continuous there because what? Yes?
At where x equals a is not part of the graph of f of x.
Yes, and the limit as x goes to a of f of x is, in this case, what's the limit as x? In this case, let's say this is y equals L right here. What's the limit as x goes to a of f of x? L. And let's say this point right here was, I don't know, let's call this y equals k right there at that point. A little different eraser now. What is f of a equal to? K. F of a is equal to k. K does not equal L. So is this continuous at a? No. The limit as you approach a is L, but is the function value L at a? No. What is the function value at a? K. K is not equal to L, therefore it's not continuous right there. Are there other ways to break it? Well, let's talk about this. What about this? If I did a sharp turn, is it continuous here? What do you think? Yeah, it is. The limit from each side is this y equal, I don't know, j value. Sure, the limit is still j. It doesn't matter if you kink that thing. It does not matter. That will come into play later with a different topic we cover, but for continuity, just remember, if you lift up your pencil, not continuous. If your pencil is down, it is continuous. It is continuous. Tangent x. Is that a continuous function?
No.
Yeah, it is. It's a continuous function because at every value in its domain, is it continuous? Yeah, it is. Is that function defined for all values? No. Where's tangent undefined? Where cosine is 0, and that's at 90 degrees. Exactly, right. So tangent is not defined at 90 degrees. It's not continuous there, but the point is it's not defined there. You understand what I'm saying, everybody? So, for example, this has come up before. We said, hi, tangent, very specifically, is a continuous function. But when you graph it, does it look continuous? No, because there are gaps. But those gaps are not part of the domain. They're not part of the graph. They're not part of the domain. They're not part of the graph. The log of a negative number. So we know that x must be what? Greater than 0. Can't be 0 because you can't take the log. Now here's the trickiest part. This is what this entire question comes down to. What's the domain of tangent inverse? Does anybody remember what the domain of tan inverse is? Tan inverse, what does tan inverse mean? No. No, it's not. To the negative one means nothing about power. This means the inverse function of tan. Do you remember this? Do you remember what tan inverse looks like? Yeah. No? Let's graph it for 1 second here.